we've got Florian and Angelo coming up to talk about how we can do better with languages beyond C. So we're going to come up and plug in and get going. We're going to give them another chance of lashing for us decompiler developers. We can find all the things that we're still not doing that we could instead. So go ahead and welcome Florian and Angelo.
Yep.
So,
Oh.
presenter view. So we are not just continuing the theme of like decompiler optimizations. We're also continuing the theme of puns based on like deep water navigation. And we're talking about languages beyond the C language. So first off, I'm Florian. I do applied decompilation research at the Athenian National Research Center for Applied Cybersecurity. If you're wondering what applied decompilation research means, don't worry. I made that term up because it feels like I'm also doing decompilation research, but I'm more trying to scale this and deal with all the annoying problems that crop up in practice after people like Zion did like the important underlying theory. The context in which I do this is basically using the ideas from decompilation to scale up and simplify client analysis problems. So we do things like privacy analysis, compliance analysis, and questions like, does this app use an insecure crypto algorithm often boils down to constant propagation because the question is just, well, are they passing the constant for MD5 to this crypto API function? And you can basically reinvent the concept of constant propagation for each of your client analyses, or you just do it properly once, and all of this gets a lot easier. What I'm going to be presenting with Angelo is like based on my work as I do as a job, but it's also based on the open source work that I did together with him.
Hi, I'm Angelo. I'm an independent security researcher and software engineer. I'm the founding member of Reverse Apple, which is a reverse engineering organization targeting the Apple ecosystem. And I'm also a noob speaker. This is my first conference ever.
Yeah, for context, Angelo did much of the underlying work that needed to be done and code to be written, while I was like the ideas guy and didn't actually do that much and just told him what to do. But this wouldn't have been possible without him. So, first off, this isn't actually an iOS talk. I'll be talking about Objective-C and Swift, but what I find much more interesting is all the problems that crop up if you're dealing with a language that your tool developers probably never really saw. For example, Objective-C is a very niche language overall, but if you're in the iOS niche, it's everywhere. But you might not be able to share your samples if like we're doing app analysis from the App Store, so we can't, like, these are all copyrighted. We can like do the analysis, but we like can't just send the binary to someone. So if I run into a bug, I'm pretty much on my own. And this is also like relevant if you're doing vulnerability research on any kind of weird targets, where like telling somebody that you like need this feature or this weird processor might already be telling them that you're like looking at this target. So like being able to deal with foreign problems, languages, CPUs is relevant beyond just if you enjoy tool development like me. The goal for this talk is basically get you away from the sense of your decompiler is a magic black box that sometimes produces good decompiler output and sometimes it doesn't, and more towards the frame of mind that this is like a tool you can adapt and extend like any other tool you have in your toolbox. Like if your Frida script that you found online doesn't quite work, you can write a better one. If your decompiler doesn't quite work, you can write better analyses and often just plug in the results back in. But this then boils down to choosing the right or the appropriate tool, and in practice, there are relevant differences. I'll be focusing mostly on Binary Ninja and Ghidra because they feel like the most user-friendly to me, especially Ghidra, given that it's open source. And I'm like kind of splitting this into 4 levels. Like sometimes there's a straightforward API you can use, and this was like clearly intended to solve the problem you currently have. Sometimes there's a general purpose API you can use, but this will have overhead, and maybe you'll need to build a feature that another tool just has out of the box as an API. Sometimes you can abuse features to make it easier, but it's clear that they were never intended to be used in this way, and you probably should just demand better APIs from your tool authors. And sometimes it's unclear, but this mostly cleared up after initial dry run, so this is pretty much not relevant anymore. But sometimes it is genuinely unclear because you might not know what the feature name is that you're looking for, which makes the searching the API a lot harder. So if you know nothing about Objective-C, if you look at it in Ghidra, it will start looking like this, which is frankly unreadable garbage. I don't think anybody of you can tell what this program is doing, and like, if you think this is just because you don't know Objective-C, no, like this doesn't help. There's nothing useful in there. But once we're done with this is going to look like this. And again, even if you never saw Objective-C, suddenly there's a ton of information. And when I was starting this talk, I was constantly being anxious that I like messed up the screenshots because like they don't have anything in common. But we'll go through this step by step. And afterwards, we'll hopefully understand all the easy things you could do in between to get a massive difference in results. And this was all possible since around June 21, like a specific Ghidra release, and was mostly like lingering in my scripts because many of these were like 20-liners or something. Yeah. So, but for a bit of context, decompilation research can be split into like roughly 3 areas: control flow graph recovery, discovery of types and variables, and control flow structuring. We just heard a lot about control flow structuring from Zion, but if you're doing automated analysis, it matters very little that you have nice and linear control flow. So we mostly focus on control flow recovery and discovery of types and variables. Plus, if you don't have a good control flow recovery and types and variables, your linear output is still going to be fairly useless. So Objective-C is an old language. It was like initially developed and designed in the early 80s as basically the pitch C, but with objects. Every valid C program is a valid Objective-C program, and then they add a bunch of things on top, roughly. This started being widely used in the late 90s, and to give you some sense of the timeframes here, Java was developed in the early 90s. So this predates the OOP language that we all know and have a complicated relationship with by about a decade. For some terminology and an example of how this actually like looks in practice, it uses square brackets all over the place for something called dynamic dispatches. These are method calls similar to method calls in like higher level languages like Python or Java. And the important terms that we'll be using is like the receiver is basically the this argument from C++, and it receives a message that is called, like that has a name, which is a selector, which already is quite convenient because these method names are like available all over the place. Yeah. So we start from this. How do we actually get to something readable? The first thing here is that to your naive C or eyes that are used to regular C, you might think, oh, these are like regular function calls, the functions we haven't reversed yet. But this is actually false. This is a weird concept Apple introduced to hide all the dynamic dispatch message sends into separate functions. This is kind of new, and my best guess is that they did this for CPU caching and branch prediction reason, but I'm also, like maybe they just did this to mess with us. The solution is fairly straightforward. They're like conveniently all placed in a specific section with a specific name. So we just get the simplified P code for this. We find out the selector that's being referenced. We rename the method according to the selector. We move it to a separate namespace, so it's later clearer that we're calling the stub method. And we fix the signature. Like we can do like the exact amount of arguments based on the selector, but in practice, you can just declare it as like variable arguments, and Ghidra does all the work for you. the result is this. We now have method names. Now it's clear what is being called here. And Ghidra starts inferring the actual arguments, which already reveals that there are specific constant parameters passed to this that before were not apparent in the decompiler output. In terms of tool feasibility, this is something that has existed for years. Pretty much immediately after this came out, people were probably writing scripts. If your tool supports any kind of IR, this is straightforward to write, and even if it doesn't, you can just find the only string reference in this function, and it's probably the selector. Next up comes the automatic reference countering. This basically, because this is a garbage collected, or it is basically a garbage collected language, but uses a fairly simple system for this. These are all inserted by the compiler, so you don't see these specific methods if you're writing code, but they're all over the compiled output, and they completely mess with Ghidra's or any decompiler's ability to do their work. Worst of all, they can even implement things like loads and stores. So they write to memory in a way that's opaque to your decompiler, but was just regular shuffling around of stack variables to the compiler. They are basically irrelevant if you're trying to understand the application level logic, but they might be relevant for certain kinds of bugs. And it's not something that you'd want to completely hide from a user. You still need to be aware that these exist. But dealing with them brings us so much benefits that, well, dealing with them is worth it. But how do we deal with them? Ideally, we could just replace them with summaries that represent the actual logic of what they do, minus all the annoying reference counting. And it turns out Ghidra has an obscure feature for exactly this. Back in June 21, the Ghidra debugger was being released, but as a pathological user of static analysis, I have, I think, never actually used the debugger. And in this release, there was something else that I was way more interested in. Deep in the patch notes, they had this message: support for program-specific extensions to a compiler specification. This feature that allows us to replace calls has existed in Ghidra at least since the public Ghidra 9 version, but it was an absolute pain to use. You had fork the entire thing, copy the entire architecture specification to then just add these compiler specification summaries. And with Ghidra 10, they just made this an API. In true government software fashion, it's an API that takes an XML string. In their defense, the underlying files were XML, so this is the most straightforward way to actually add this. What this allows us to do is we specify the name of the call fix-up, so in this case, Objective-C load weak retained. We specify the target, which is the actual function name that should be replaced. In this case, it's just the same name. And then we specify the P-code summary that we want to replace this with. In this case, x0 equals dereferencing x0, so load the value behind x0 as a pointer and store it in x0, which is just the memory load. Because writing XML by hand is annoying, we can put this into a dedicated function in Kotlin that now takes sensible arguments and constructs us the XML string that represents what we want. Afterwards, we can just write things like this. We give this a name, we give this a summary, and we just give this all the list of methods that should, in this case, just be replaced with a knob. Because if you ignore reference counting, they just do nothing. But they do nothing in a way that the decompiler should know about, because it allows it to do much better optimizations. In practice, this is the difference between originally this and afterwards this. Half of the code just disappears, most variables disappear, and suddenly you're left with what is only the actual program logic happening in this method. Ghidra can do this via this API. Binary Ninja can do this via the workflow concept that they introduced in 24, but apparently there's the running joke that Binary Ninja can do everything with the workflow concept if you just build on top of it. So I'm counting this as you can do it, but it takes you probably, I don't know, a day or two to figure out how workflows work instead of just solving the problem you were actually trying to solve. But bonus points for Binary Ninja, they make it a lot easier to toggle workflows on and off. So we're left with just this. This is like classical access of members of a structure. This is a problem all over C and C++. Dozens of papers have been written on this. It's a giant headache. But it turns out for Objective-C, it's actually way easier because there is a lot of useful metadata that Angelo will now tell you about.
Hello. All right, so this is the main class metadata structure that Ghidra already parses. It mainly contains the meta class and superclass pointers right there. So, and this mostly describes the relationships of the class. But let's go further. So I'm going to be jumping around a lot, so I put breadcrumbs in the upper right corner there. So we're going to be jumping into this RW field right here. So this will lead us to the RWT structure. And this basically contains mutable class data, hence the RW. And what it does is it contains more of the contents of the class, like methods, protocols, instance variables, and properties. It would be useful if we had a model for this. So how about the class concept in Ghidra? Well, they're literally namespaces. So basically, what we did is we rolled our own model that is specialized for all Objective-C language constructs. And basically, it ties class T and class RWT structures into one unit. We also wrote modern type, property, and signature parsers. So all of these are now parsed in one pass. So parsing metadata now, it gives us an accurate object model for any Objective-C binary. And it also includes a nice API for method resolution, which I will touch on how that helps in just a bit. But let's look at a basic decompilation example here of an Objective-C method. So this is just a property accessor. So you can see here a member of parameter 1 is being set to a value. But parameter 1 is actually a pointer to self because it's an Objective-C method. So what we can do is we can represent our animal class as a data type. And let's see how we can do that. So this is the IVAR list structure, which is right off of the RWT structure. And basically, each entry here represents an instance variable that includes an offset, a name, and an encoded type. We can start by reconstructing this data type by decoding each one of these types into their, like a Ghidra data type. And from here, fitting these into a structure is pretty straightforward. But you might notice that up here we have the first field. I'll try and zoom in on it here. The first offset here is, starts at 8. And what this is, there's an implicit pointer here that it's called ISA. It points to metadata, but it's kind of nebulous and could also encode flags. I mean, but either way, it's very, very rarely used outside of the runtime, so marking it is usually redundant. But so when we do this and apply it to parameter 1, we go from this to this. And as you can see here, it's no longer just a bunch of pointer arithmetic, it's an actual structure access. So what else can we achieve with this model? So we have here extended signature recovery. So Ghidra's Objective-C signature handling is pretty mediocre. There's nothing wrong with it, but the issue is more with how signature types are placed in regular method T structures. They're just not detailed at all. But fortunately, we have protocol metadata here, and this contains a field with a bunch of type-rich metadata signature or method signatures. For those who don't know, protocols are basically just interfaces in modern OOP terms. And despite the comments above it, this field appears to almost always exist. So consider the following. We have an example here that was found in the wild. This is a class TA controller. It has a method, TA receipt request, did complete with receipt. The signature here is, it works, but it lacks detail. And we can actually improve this dramatically with our new knowledge. So let's see how we do that. We parse our class T into our model. What we do is we then resolve the methods by analyzing the protocols and superclasses. And then from there, we can isolate the declaration implementation stack for the method in question. And what this does is it basically allows us to easily answer the question of what declared this method. So like trace the origin. So let's go ahead and apply this concept as an analysis pass. So what we do is we resolve the method. We ask ourselves, is it declared by a protocol? And if the answer is no, we just use the method T signature, which is not, again, it's not incorrect, but it's not detailed at all. But if the answer is yes, then what we do is we ask ourselves if the extended types list exists, which it probably will because every time I've seen it, it's had it. And if the answer is no, we just obviously go back to that. But if the answer is yes, we can just use that signature with all of the rich types. So let's take a look at the result of doing this. So this is the before, and this is the after. And those parameters, by the way, are also renamed algorithmically based on the selector, just a bonus there. But yeah, this is automatic. And what's crazy, no other tool appears to take advantage of this. So now, let's talk about categories. Categories basically extend the class functionality without inheritance, but they're not necessarily bound to one class. And I'll illustrate that with an example here. We have two classes. We have a dog, and that inherits animal as an abstract class. And each of these things have their own method lists. And now let's introduce a category here called dog training. It has its own method list, but it's only accessible off of dog. And basically what I'm trying to illustrate here is a category can have the same name, but apply to another class. So let's do the same dog training category, but applied to dog owner. You can see it adds different but relevant functionality to the category name. But let's take a look at this concept in metadata form. So this is the metadata structure. You see the name of the category and the class it targets, along with all of the stuff it implements for that class. Now here's what Ghidra produces. There's unmarked data everywhere, and it weirdly appears to stop parsing at null fields, which is not how you parse structures. But weirdly, it doesn't do this for the other kinds of metadata. Like the other like class T doesn't do that. But here's how it should look. So we saw that bad parsing basically excludes entire method lists and protocol lists. So even though categories aren't frequently used, incorrect parsing disrupts analysis when they are in ways that is not really expected. So let's take a look at the causality here. So when categories are parsed incorrectly, it causes unmarked method lists, which obviously leads to unmarked method entries. And then it can lead to either of the following. It can lead to functions without metadata, as well as completely undisassembled functions. So you just like that they aren't analyzed or disassembled in any way. They're just spans of bytes. But basically, this is something that we are actively working on, and we will support in a future release. But these were the two big results we were able to achieve. We've achieved unprecedented method signature analysis enhancements and full object structure data type recovery. We've also achieved a number of other features like method insights and property annotation. But that's about it for me. Back to you, Florian.
Yeah, so to recap, we didn't actually need to do much for this improvement. It's like one API that you need to pass the right XML strings to, use an existing parser that for the most part Ghidra already had. Like all this instance variable metadata, Ghidra was parsing this. Like somebody sat down, wrote the parser, knew that there was all this information, but then didn't use that to just create the structures. You don't even need to do any complex calculations for this. Like all the metadata already tells you like the exact offset, it tells you the type, it even tells you the size, and from that on it's again one API call. For the message send stubs, straightforward AR analysis, so not hard either. But we can see that this is like already something that would have been harder with Binary Ninja. Binary Ninja could have done this, but you would have needed to spend time building this whole call replacement feature. And as funny as it is that it's like an XML API, I can't accidentally segfault myself by passing an XML string, but I can if I need to write like a workflow rewriter in C++. So that leaves us with control flow graph recovery, and when academia kind of starts becoming useful, somewhat, at least your pedantry. So for context, dynamic dispatch is kind of the cousin of, or like dynamic dispatch is the parent term, and message passing is somewhat the cousin to virtual dispatch. So C++ has their virtual tables, which then leaves it with weird offsets in your code. But in Objective-C, it is just a standard runtime method being called with a receiver object and the name of the method that this object hopefully implements. Objective-C uses this everywhere, even for references or like calls on static classes that would have been like clearly able to resolve at compile time. It's still a message send at runtime. And again, interestingly, Ghidra has a resolver for doing this, but it's brittle, but it gives you the information how to actually achieve the result. So if you're looking at this on the left side, it's like the regular dispatch call, how it looks if you decompile this. On the right side, it's after this Ghidra analysis ran, and it shows you that there is a call to the send location function within the location helper class namespace. This is where like classes being namespaces becomes useful because you associate a method with a class, and well, it just works like assigning it to any other namespace. But how does Ghidra actually decide what to render here? Turns out, again, there's a fairly simple API for this, and they have a concept of primary references. And this simply seems to decide that if there are like multiple references to functions at a given call site, which one of those should be used for the purposes of rendering. On the right, this is how we use this. This is like a nice Kotlin feature where you can pretend that like a method already exists on an existing object, like basically categories. So we can just add a method when we have the information that at a given call site, we're calling a like given function that we resolve with our model, and we apply this. So first step, we just expose this to users. It's fairly straightforward to write a simple dialog that you can use or like pop up for any kind of message send call, and just allow the user to decide which method is probably being called here. We can do some pre-filtering simply based on the name. And because Ghidra has abstractions for basically this case of show a user a table and then call this callback with the result they selected, this is, again, straightforward. Nothing prevents you from like adding wrong references here. But at least if you want to decide that you're pretty sure that it's always calling this, you can just add this, and you have clickable references if you want to come back to that place later. The result is shown at the bottom instead of, again, calling the batched bridge method in the stub namespace. It is now just calling the batched bridge method in the RCT bridge namespace. But we still see a bunch of casts here. Or no, not that yet. Again, Ghidra makes this straightforward. Binary Ninja can do this by, well, doing a workflow for it and rewriting the actual call. Again, like if you're writing your workspace workflow already, you can probably add this, but it's again something where you have extra overhead, and the Ghidra devs seem to have like thought of this already. Interestingly, the Objective-C analyzer that rewrites this is the only place I found in the code base that actually uses this concept. You can also use it via the UI, but it is hidden behind like 3 levels of context menu, and it's hard to find even if you know it exists. But like this is obviously applicable if you're doing like any kind of C++ analysis. Like if you have some kind of virtual table resolver that finds out what specific methods could be called here, you can use this method, add the references, and if it's just one, it's just rendered. So if we now actually want to start resolving the dynamic dispatch targets, we run into object-oriented problems. Because if you see a call that some animal is biting a person, it makes a huge difference what kind of animal is doing the biting here. In practice, for like actual code example, this can be cases like you have some logging functionality, and the question is this logger the kind that like logs to the network and potentially leaks sensitive information? Is it like the null logger that just kind of does nothing, or just does it log to like a local std out or something? Same for like general purpose, like if it's something we can write to, it's again, is it a local buffer? Is it a remote thing? What does it do? And as far as I can tell, neither Ghidra nor IDA really account for this. They will just, if they see this has the type animal because it is, for example, like already a method in the like animal namespace, it will just rewrite this to the animal method and not give you any hint that in practice there might be like overridden implementations of this. So the Objective-C type system is overall fairly simple, but it is still more complex in a way than the C++ type systems would be. We have inheritance, but gladly it's only single inheritance. We have lots of protocol usages, but these aren't complicated either. And as we heard, like they give us really beneficial data too. We have categories, which are like a thing you need to think of and parse, but at that point you also know, well, if there's a category that this method, you just need to like go there. Or you need to like stop the search because then you know this specific method is the one that implements this. Where it gets weird to think about is that Objective-C is statically typed in the sense that C is statically typed, but you type something as an object, and then these objects are dynamically typed. So you don't necessarily know that just because a message send call happens with a specific selector on an object, if this object even supports the selector. This might just crash in runtime, like you can shoot yourself in the foot with Python. But this also means that like the leftover problem is like a classic dynamically typed OOP language problem, which isn't something new if you're, well, doing the classic kind of static analysis as the software engineering people would do. But the problems you run into here are that if we want to know the message send targets, we need to know like the precise receiver types at a given call site. To find out what these types are, we typically need to trace them back like to the return value of a previous dynamic dispatch or an argument of the current function we're looking at. But the problem is that we don't have the types for parameters for a message send call in many cases, if they're like not protocols, which means we need to look at the call sites to see what kind of objects are being passed in there. But we don't know the call site of these methods because we don't have solved the problem of correctly identifying the call, like the targets of dynamic dispatch calls, which kind of means we're going in circles. But we can just start with the simple cases for now. In many cases, there are no subtype shenanigans happening. There's just an alloc of a certain class and methods being called on it afterwards. So the solution for this is, again, fairly simple. We iterate over all message send stubs. We just decompile the method, and then on like we decompile it and like take the SSA P-code form that the decompiler provides and just walk backwards to an alloc call, and then we know it's like definitely this type. we take this class, we search our model for the implementation that will provide the actual underlying code for this specific class and this selector, and we add the reference to it. This backward slicing is very easy because we removed all the arg fix-ups earlier. So we don't need to add like any special handling that, okay, this was the return value of like an Objective-C retain, which means we now need to get the argument. This all disappears, and typically it's just one step back, and we have the alloc call. This covers all class methods in the same way, where it's like instead of walking back to the alloc, we just walk back to like the reference to the static class. And if you're like being very precise, it only covers the constructor calls, because then you have a dynamic dispatch to another method. But in practice, you can just assume that if you're like calling a constructor, it is just returning the same object again, because that's how the constructors are defined. So we know what the underlying class is again. These allocs also give us more useful metadata, or like we know the type at this point, and we also want to like recover our variables and actually give them like useful types and split them correctly. Turns out Ghidra again has a feature for this. It is like hidden in the context menu, and you probably saw it if you like ever used Ghidra, and it's the specific override signature action. With this you can define that this specific call at this specific call site has a different signature than the underlying function would usually have. We just automate this via the API and just set these for all, and Ghidra starts typing correctly. An important pitfall here is that you don't want to like type the return, or the variable that we assign to, which you could also do, because this then breaks Ghidra's variable recovery, because it only like affects a variable that Ghidra has already inferred to exist, but this might be wrong or like insufficient because the types weren't correct and all the variables were merged into one. So you need to do this via this API to get good results. This is something that Binary Ninja also just supports. They have a dedicated API for this. So straightforward there too. So again, we inject this. Because the arg calls are removed, this propagates fairly straightforward. And overall, we now have like a lot of metadata to actually get useful types for variables. Every kind of alloc call gives us information, and because we earlier created the structs where the members have type, Ghidra starts doing the regular type propagation based on like the types of struct members. And yeah, variable recovery is a lot nicer because they are simply split by types, and you don't need to do this by hand either. So back to the whole call graph problem. Another easy solution for this is we just give the user the choice to make their own decisions again. So for our call sites to a dynamic dispatch, we just recover the selector. We store this method name somewhere, and we want to store it because this takes a while to compute. You don't want to do this every time like you reopen your tool because you only stored it in RAM. But the problem then again is, where do you store this information? Ghidra, again, has a dedicated abstraction for storing a mapping from an address to a primitive type, so basically a number, a bool, or a string. And this handles all the underlying pitfalls for you, up to and including version tracking. So this gets synced to the server if you're like using the Ghidra server, and this apparently even handles merge conflicts between users. Binary Ninja has general purpose storage, but then you kind of need to roll this whole concept on your own again. You need to deal with your own versioning, but it's not as much work as the other features. And from a UX side, it's then, again, you just give the user a context action. It pops up a table, and they can just click on this and jumps to this, similar how you would do this like in a classical kind of IDE. But an important pitfall here is you don't want to add this as a regular call because you're just making inferences, and you might later have analyses that rely on only dealing with calls that are definitely there and not calls that might exist purely because the name happens to match. This is something that could also be supported in a nicer way by like allowing different kinds of CFG models and different kinds of approximations, but this is something I've like never seen in any kind of interactive decompiler. Intra-procedural type analysis. We now have type information from all structure fields, getters and setters, because these are very trivial to infer, because it's just a method that acts as an underlying field, so we just retype these methods. We have all alloc calls that inject this, plus there are like a few other cases like singleton patterns where we call shared instance on a class, and this well returns an instance of this class. Same process as before, we can type this correctly. And on a large data set on which I evaluated this from like 2,000 apps from the App Store, this covers around 60% of all call sites, where you then know like at least a type bound for the receiver, and you know the method name being called. There's still a bunch of edge cases where this gets hard, but it works well enough. And most importantly, intra-procedural analysis is embarrassingly parallel. So if you have 2,000 methods, because you don't need to deal with how they interact with each other, you can just parallelize this across many threads as you have. This is something where, like, if you're doing headless automated analysis and this like runs for 2 days, whatever. If you're doing like interactive analysis, you don't want to wait 2 days until you can finally start using your tool. So, but what about the edge cases? Because of compiler optimization, sometimes basic blocks get merged, which means the message send call sites get merged. So in one path, you might see like a specific kind of dog, the dachshund being allocated, and the other one, the shibu, and both of them then like should bark. This is, like, from an analysis point of view, this is fairly easy, but from a practical point of view, this is annoying because what kind of reference do you add at this case? You can add both, but then it's like not clear anymore. And ideally, you could like split this call into like 2, and you would have like 2 locations that then have the reference, and you just see 2 calls in like your actual control flow structured output. This also exists for the other case where it's like, okay, it can be 2 different selectors, but all the same object, similar problems. Annoyingly, in very, very rare cases, and I think it was around 3 instances of this across a data set of 10 million message send call sites, the compiler does both, which completely trips up IDA. Binary Ninja here goes with the conservative interpretation, where at the bottom we can see the Objective-C message send call that calls this, like, has a receiver that is either the NS bundle main bundle or the APM measurement identity, and then the selector is either bundle identifier or app ID. IDA, for reasons I do not understand and are probably a weird edge case in variable typing, hallucinates a method APM identity bundle identifier. So it like takes the selector from one block and uses the type from the other one, and then assumes that this method just exists and creates as an external one. I have no idea why, because I can't look at the actual code. But this is, I guess, one of the trade-offs that happens if your decompiler like relies on heuristics. Like most of the time, IDA just has better decompiler output because they, well, take shortcuts that go wrong in ways that you don't necessarily find if you don't have like an assert in your analysis engine that this like combination never happens. And for the longest time, I assumed that like this would never happen, but it does. And if you scale up, you get crashes. So I'm still beating around the bush around inter-procedural type analysis because it's hard and we're still currently working on it. The type system isn't that complicated in Objective-C, but it has inheritance, and that's something that most or all inter-procedural type analysis algorithms that are like publicly available do not handle. And if they exist, they're like specifically for C++. The P code that we're dealing with is fairly simple because we have a lot of extra information, removed all the arc methods. So this should overall be doable, but this will take some time. And in this case, I'm like estimating this will take a month or 2. But luckily, I'm not a malware analyst. So what would be like a horrible waste of time if you're doing like threat intel is literally just my job. And the only price I pay for this is that I have to write it up in a like archaic 2-column PDF format afterwards. But at least I get to solve like problems properly. So in retrospect, Objective-C is overall pretty solvable. There are like some challenges left, but they aren't like conceptually hard. And even the interprocedural type inference is basically just what Java program analysts have to deal with for like ever. And luckily, where I work, I actually have colleagues who have been like dealing with Java program analysis for the last 10 years, so I can just ask them and don't have to like reinvent all of this myself. And we currently are exploring ideas if like maybe we can just reuse existing tooling there. So maybe this is just something where like we plug this into existing tooling and this entire class of problem is solved because we can build up on previous research. Or we just port this over to Ghidra. Yeah, but again, something that was easier in Ghidra. We had our like existing feature to add these references, and the arg removal is probably the biggest deal. Like for any kind of analysis that you want to do later, you could like reinvent the summaries again and handle this, but this leads like to a lot of duplication of the exact same logic. Then you find a new arg method and you need to add it like in 5 different analyses and add domain-specific summaries, and it's a pain. So, Swift. As always, in a modern language, they break everything, including strings. But there is not much of a way around this. Like, we did measurements on this from like the top 2,000 apps in Germany. Pretty much every app uses Swift in some form nowadays. And this hasn't always been the case. Like 5 years ago, it was like 70% of the apps. And because it's hard to distinguish how much Swift they're using exactly. This includes apps that, for example, just use like the standard Swift networking library instead of like the old Objective-C library. But because you can mix Objective-C and Swift in like one app, this is something that we need to deal with. The very basics of Swift are, like, to roughly summarize, control flow is more complicated than Objective-C because they do all the classical things that like a modern C++ compiler would do. You can like inline methods, you have direct calls on like static methods, you have virtual tables, and you have message passing because they want to be compatible with Objective-C again. But from like a tool integration perspective, this doesn't actually pose a new challenge. Like, yes, we have to then analyze this, and it will be harder because the easy cases were all optimized out by the compiler, hopefully. But once we have this, it's the same API as before. Where it gets tricky and interesting, why I included this, is they also have weird strings. There's basically, for a basic string, there's 2 cases you can run into. There is the pointer version, and there is the inline version. They look fairly similar. In both cases, it's just like a struct spread across 2 registers, and the first nibble indicates what type it is. And in the pointer case, we just have the pointer, but just to like insult us, they also add some bit in the top bits to make sure that Ghidra, like the tools don't recognize that this is a pointer. And for the inline version, it's just the leftover bytes, like the leftover 15 bytes that are available in these 2 registers are the inline versions. Again, from an analysis perspective, this is easy. Like, if we know that it's a string, which we can do with type inference or some simple pattern matching, we would just like, well, we know either the pointer or the values. We could just like rewrite this and show this, except we can't. This is one of the limitations that Ghidra does not support. Binary Ninja probably supports it as of a few months ago with their new pseudo language feature, but I didn't have time to integrate and look at this. You can maybe kind of hack this with Ghidra by abusing the enums, and basically for each string like this, you add an enum with the same value that then has the name of the string that's actually inside of it. But this horrifies me and I refuse to implement it. Because this is one of the things where Ghidra has weird design choices that probably made sense 20 years ago, but are now starting to severely limit us. So in the top left corner here, you can see the regular decompiler output that you usually see as the end user. This is like some C code. Those are like old screenshots from me. On the top right, you see like the decompiled P code. Also fairly simple. You see the 3 calls, you see the direct arguments. And at the bottom is the syntax tree which the decompiler the decompiler process returns to the JVM process. There's no rendering for this by default. I like wrote a plugin for this back when I was young and naive and hoped I could do some cool rewriting things. But if we look at this more closely, we start seeing weird things. Because if you ever dealt with IDA, they give like a nice abstract syntax tree with concepts like, hey, this is a function call, this is the first argument of this function, this is the second argument of this function. Ghidra gives you a token stream. This includes elements like parentheses, which means if you want to do anything useful with this, you need to first write a C parser, and I don't want to write a C parser. I have no idea why they exactly do this. It might be easier for some cases, and it is possible to patch Ghidra in a way where you can start rewriting this, but I wrote this up years ago. I posted in like the forums. I never quite got a response, and this is the kind of patch I don't want to maintain. And again, you can get the actual syntax tree, but then and the infrastructure in place for rewriting it. But at that point, you then need to build all this infrastructure, and this would probably be a lot easier if they like had support underlying for it. Binary Ninja. Well, they have a pseudo-language feature, and I think Swift was either an example they had in the blog post, or I think something they had in mind, at least when I talked to them about it. And this would be like an obvious first prototype for dealing with these kinds of strings. Yeah, so overall, in terms of tools, we got massive improvements with a few simple tricks by just knowing how to use the tools correctly. Which means that like the choice of the tool you have has implications that are not necessarily obvious to you at first. Like in practice, Ghidra, I don't know, looks uglier, has a worse decompiler than other tools, but in the underlying design, it starts to suddenly have advantages that make it a lot easier to adapt it to the weird things you're dealing with. From the underlying design perspective, I think this comes from that like user plugins are like never second-class citizens. So everything you write can use everything that is available. And there's never a case where it's like, the tool clearly does this, but the API for this isn't available. Maybe if you ask, you get it in the future release. Unlike Binary Ninja, also I can never segfault myself. And I will like go out on a limb that I actually write JVM languages and enjoy it. But there is Kotlin. I don't like Java. So yeah, in terms of languages, for me, the recap for this was new languages aren't inherently hard. Like Objective-C looks intimidating at first and very hard to read, but in some cases, nobody has solved it yet, or nobody has publicly solved it yet, but you can just solve it yourself without too much effort. Sometimes the kind of effort is like actually research, and like the academic kind of research that takes far longer timeframes than what can like be justified if you're doing like threat intelligence. But luckily, there are people who are well paid to do this. But these people are like not necessarily the tool developers either. So like, I need open APIs to do this kind of work. And if they make it very easy to develop extensions, they also make this a lot easier for me. For Swift support, we're currently working on this, but it looks like it might also be fairly easy. Like, I currently have a student that like is looking into Swift and all the underlying details, and there's a good chance that I can do this talk in like half a year, and it's like the same idea of like, okay, we have metadata, we can rewrite this, we can write analyzers for this, we can just rewrite this. We can, well, if we have Binary Ninja or Ghidra maybe hopefully adds this feature, we can start rewriting strings to actually be useful, then adds proper string references. But this is something that's in the pipeline, and I hope I can present more on this some other time. Yeah. Overall, thanks for your attention. If you want to like check out the plugin, it is on GitHub, but it is currently very much in a process of development. So we're basically looking for people who want to like give this a try and like actively work with us so we can like understand like the kind of features you want to see in it. And we can like walk you through like the design a bit. Because there's a heavy churn on it, it's not much documented yet. So yeah, overall, thanks for your attention, and we're now open for questions.
Test.
Thanks for the talk. Love it. One of the things you guys looked like you were using was the metadata to kind of infer a lot of information about the structure. You mentioned that most cases have it, and I was looking at like a Golang binary, and it was it has similar metadata, but that was also like kind of, I don't know if I say it's similar metadata, but it was stripped. And I assume that malware and other people who are trying to obfuscate their code, can they strip that as well? And what does that look like for what you guys are doing?
I don't deal with malware, so I don't fully notice. Like in practice, because apps are encrypted, developers don't seem to care. Some of them do, like some rare banking apps start obfuscating things, but the only thing they seem to be obfuscating are the selector names, but just replacing them with different useless strings. I think because of the way that the runtime works, it does rely on this for at least some features. So you might be able to strip it, but then run into like crashes. But my goal with this plugin was basically deal with the simple apps first, because if you're doing malware analysis and know that like every regular app and developer has this information in, an app actually going out of its way to strip this is a giant red flag. And I think the code we have just or like at least other code we have that analyzes app just loudly crashes if this is missing, and I don't think I have seen this in like any normal app ever so far.
Makes perfect sense.
Any other questions? I'm coming, Martin.
Thanks. Like I'm generally a lazy person that dealt with iOS and everything like 40 years ago. But what I always did is I just took my old Hopper disassemble license and it did all that 4 years ago. Have you checked that as well?
Yeah. You checked this at least for the extended prototype?
Yes, it does not do that.
Like when I was comparing that 4 years ago or 3 years ago to Ghidra, it did what you showed afterwards much. It like those object sense and all these things it seemed to do. But maybe it was that change that you said that Apple introduced to that wrappers to these object sense. I don't know. It was really like 4 years ago when I looked last at iOS binary.
To be fair, I haven't looked much into Hopper because it is like a specialized tool, as far as I know, mostly for macOS. And because I do automated analysis, not necessarily like end-user facing decompilation, I have no idea how well Hopper works for this. Like, do they have an IR? Like, did you ever deal with this?
I try to not deal with Apple things, so it was only when I had to.
Fair.
But thanks.
Yeah, like given that much of these things were easy enough, I can plausibly imagine that Hopper did much of them. But like part of why I wanted to like structure this is like not an Objective-C talk, is the like, this is, I think, extensible to Golang. Like Golang has metadata, and maybe this got better over the last years, but for Golang it also at some point sounded like the best we can do is strings, and everything else is still horrible. And I hope that like this can serve as a guide for people who are dealing with other languages, who can now like understand how to add the information that is potentially there or you can like acquire.
Yeah, thank you.
Any more? All right. Thank you, Florian and Angelo.
Thank you.